All right, today we're going to talk about trusses and the method of sections. So the last lecture, it was one from a pre-recorded one, but it was about trusses and method of joints. And the idea there was that you could look at a truss, so like a 2D, it would work in a 3D truss too, but we were looking at 2D planar trusses, and you could go joint by joint. So where the truss members were connected together, you could go look at each one of those joints and solve for the forces in each one of the truss members. And that's fine if you want to know something on maybe the perimeter of the truss where you don't have to work your way into the inside of the truss, or if you have like a reason that you want to solve for every member, then also makes sense. But sometimes you may only want to solve for a little piece, a little interior piece somewhere. And so the method of joints in that case is cumbersome to get all of that done. And we have this thing called the method of sections. So it does rely on a new concept that we haven't talked about yet. So we have to do that first. Then we can kind of review trusses. And then we can apply the method of sections. So the new concept is going to be called moments, torques. We're going to call them moments, and we'll go down to the page here and look at what a moment means. So in engineering, you have this idea of moments and torques. So in physics, it's really all just torques. And moments and torques are the same thing. We just name them differently to talk about specific use cases. So a torque for engineering is going to be a force that's applied causing some kind of rotation about a shaft. So like an axle or something like that. And I'm trying to twist the axle, or I'm spinning a wheel around the axle or whatever. And I'm applying a torque in that scenario. We actually will do some torques in the last third of this course, so we'll do some torques. And a moment is going to be the exact same thing, but the outcome isn't that I'm really twisting, like I'm not intending to try and spin something. It may be the result, but it's not the thing I'm trying to do. And so we kind of separate out. Moments are forces applied at some distance from a application point, or some kind of center of rotation, or center of twisting, or center that is just a center. And we need to kind of develop some rules for what a moment is and how to deal with it. So the first thing that happens is that let's just say that a moment equals a force, so some kind of force vector, multiplied by a distance. And I'm going to be particular about the distance, and it's going to be a perpendicular distance. So it doesn't have to be that it has to be a perpendicular distance in every case. You can do vector math and just have a force and a distance, the two force vector and the distance vector, and you can calculate a moment. We're doing everything in rectangular components, so x components and y components, and in that case it's going to be much simpler on us if we think of, I'm looking for a force, and that force is creating this moment effect about some remote point, and I need the perpendicular distance between that force and the point I'm interested in. So this could look like, let's say, here's the point I'm interested in. Right now, the points are literally going to be dots. They can be objects and free body diagrams and all that kind of stuff, but for now, let's just keep them as dots. And then I've got a force. So we'll say that this is our force. We'll just call it F. And this force has a line of action. Remember, it can extend infinitely in both directions if I want it to. And the distance that I'm interested in, if I'm trying to calculate a moment, would be the perpendicular. Wow, that's sliding around on me. There we go. So the distance is going to be perpendicular to the line of action of the force. So I've got this line of action, and it's going to go through this point I'm interested in. So this is the point of interest. Over here. And there's my line of action. That right angle, that's the distance. So if I want to calculate the moment that the red force creates around the point of interest, then I would say that, well, the moment equals F, whatever magnitude this force is, 10 pounds, times D, whatever distance that, however long that blue line is, 10 inches, and I've got 100 inch-pounds of moment that this force is creating about that point. Now, I'll pick another point somewhere, and it creates a different moment about that. A force can create a moment about infinitely many points. We're usually, making these points of interest selections, strategically, and so we don't just think of any random point in the universe. So we usually have a reason on which point we're going to pick to do this. But we'll develop that as we go. We don't have to understand exactly what point to pick at any time just yet. There are some guidelines that I can show you of what's probably a good point to pick. Now this does one thing though. So moments don't exist when we have concurrent force systems, because all the lines of actions are converging at a point. So if my line of action actually goes through my point of interest, then the distance between the line of action and the point is 0. So I go to do moment equals force times distance. Distance is 0, so the moment is 0. So that's why we started with the concurrent force systems, where we had our equilibrium equations, and when we said summation of forces in x equals 0, y equals 0, z, if we have 3 dimensions, equals 0. And I kept saying that there was also another one that we would eventually need. This is the other equilibrium equation that we also need. So we also need, now our equilibrium equations become summation of forces in x equals 0. That's still true. If that's not true, then our body of interest is moving in the x direction. And we have one of those for each of our 3 directions. But all those do, these 3 equilibrium equations, what they do is they keep the body of interest, or the point of interest, they keep it from translating. But if I don't also say that the summation of moments about some point equals 0, then our body could be rotating about that point. Like it could be spinning about that point. And if we want to be in static equilibrium, then we probably can't have our object spinning. Now, there are some cases where, like, it's a shaft that's transmitting power and it's not actually going anywhere, and it's spinning about a longitudinal axis. So we'll get to that in the last part of the quarter. But our truss, like if we're talking about trusses, we don't want our trusses spinning about some point somewhere. They need to be stationary. So let's do a little example on how we might use this idea that we can calculate moments and that they need to equal 0 about some point, and we'll have to pick what point that is, and that gives us a new equilibrium equation. So let's just think of a truss, but only like the bottom piece of it. So if I'm thinking of a truss being a bridge, then it's just kind of like the road part. So it's basically a beam at that point. It could be a lot of beams strung together, but we're going to treat it as one long beam. So here, that's our beam. We have to start worrying now about how is this beam fixed in space. When we had concurrent force systems, we had cables and chains and ropes and things like that holding stuff in place, or maybe it was sitting in a little trough or whatever. Now we've got more complex structures, and we might have more complex fixturing. So there's three primary types of fixtures that we're going to encounter from here on out. There are other kinds, but they kind of all end up boiling down to one of these three. So one type of fixture, let's go off to the side, I guess. Let's move this over. Whoops. And let's talk about fixtures for a second. So the three main fixture types that we're going to encounter are pins. So I'll usually draw a pin one of two ways. I'll either draw something that kind of looks like a pin. So there's some little bracket with a bolt through it or whatever. Sometimes it would just be this little triangle that it looks like something sitting on top of it. Those are common ways to draw a pin. And what a pin does is whatever's pinned there can't move in. All right, so first of all, we're normally talking about 2 dimensions. So if you're dealing with 3 dimensions, then it can also hold stuff in a 3rd dimension. But almost all of this course and most of undergraduate stuff, these are going to be 2-dimensional setups. So we don't really have to worry about depth into the page most of the time. So what a 2D pin is doing is it's keeping whatever's pinned there. So let's say that I've got a pin over here on this beam that I've drawn. That pin keeps the beam from moving left and right, and it keeps it from moving up and down. It doesn't stop it from spinning. It could spin around clockwise or counterclockwise, and we're not really considering what it can do into and out of our screen. It's just locked into that position. So if it's keeping it from translating left and right and up and down, then a pin ends up having 2 reactions. One that keeps things from moving left and right, and another one that keeps things from moving up and down. So whenever I have a pin, instead of the pin, when I'm drawing a free body diagram, I don't draw the connections, I draw the results of the connections. So the pin has 2 reactions that I draw perpendicular to one another. So for a pin, if I'm drawing the free body diagram, I would draw maybe an arrow like this and call it AY. So the reaction, if that's point A, for instance. And I might draw another one like this and call it AX, or maybe RY or RX for reaction. So if I'd actually put those on our picture over here, it would look kind of like this. Let's copy that and paste it. So I don't want to draw it on top of the actual drawing of the thing. I want to create the free body diagram by not drawing on top of the drawing. If I drew, for instance, if I drew on top, like there's a reaction, there's a reaction. Now what that looks like, or what it could be interpreted as, is I've got a beam that has a pin and some other forces, when what I really mean is that pin is creating those forces. So I know it's faster to just draw on top of the diagrams, and maybe that's fine if you're just working a problem and you need to do it quickly. But the better way to do it is to redraw your body of interest, take away that pin, because it needs to be a free body of interest, not a connected body of interest. So it's got to be free, and that means I got to take it loose from the pin, and I've replaced the pin drawing with the reactions that the pin was providing. So it would look like that. It would look like I have these forces, AX and AY. That's what the pin is doing. I am drawing them in the traditional, X is positive if it goes to the right, and Y is positive if it goes up. That's, 90+% of the time, that's what you do. There might be some cases where it makes sense to have X in some orientation other than horizontal. That's fine as long as when you draw the Y axis, it is perpendicular to X. That's all that really matters. Okay, so that's one fixture type. Pins, they have 2 reactions. Another common one is a roller. And this one might look like it might look like a pin, but instead of it being shown attached to the ground, it has little skateboard wheels on it. Or it might be the little triangle with wheels on it. So the idea there is that the roller keeps the thing it's attached to from moving up and down, or well, whatever is perpendicular to the thing it's rolling on. It keeps it from moving that way, but it allows it to move along the surface it's rolling on. So if I drew a roller over here, let's draw it this way. And there's no like specific number of wheels. Sometimes another way that these could be drawn is just a circle, you know, like a one single wheel. That could be another way that you draw these. So when I go to draw its reaction, it only has one reaction, and it's not always pointing up. The key to it is that it is perpendicular to the surface that it's rolling on. Okay, so in our example, this would just look like this. Maybe I call it BY for point B. You know, this is point A, and this is point B, and so that's the reaction in the Y direction. There's one other that we kind of have that's not a pin and not a roller, and that's called a fixed support. This one won't really show up too much in trusses. It'll show up later in the quarter, so I won't spend too much time on it. But basically, it is like a signpost that's buried in the ground, you know, and it might actually look like that. You might have this might be a fixed support, or maybe you could have it horizontal. You know, something like that. And here, the idea is that all of the reactions occur at that one spot. So 3 reactions, and that fixed support is keeping the thing that is fixed moving. It's keeping it from moving in the X direction and in the Y direction, and it's also keeping it from rotating about that point. This curved arrow, that's called a concentrated moment. And it's basically the result of what we talked about earlier. So force times distance is a moment. So the result of that can be shown sometimes as this curved arrow, this concentrated moment. We'll deal with that a little bit more. They aren't going to show up as much just yet until we get to some new topics, though. So most of what we're going to do is going to be pins and roll. Actually, probably all of what we're going to do for the next couple of weeks, even certainly the next couple of classes, is going to involve pins and rollers, not fixed supports. So what do we do with this? So let's go back to our beam over here and let's put some numbers on it. Right now it's just a beam with reactions. It doesn't even have forces applied to it. So let's put a force right here. This is going to be a concentrated force. It's a single arrow, theoretically applied at a infinitely small point. That's realistically not true. It is spread out over some amount of space, but for what we're doing, it's a infinitely small point. And let's just say that force is I don't know. Let's make it 1,500 pounds. And we've got some dimensions. Let's say that this dimension is, let's just count, 1, 2, 3, 4, 5, 6, 7, 8 feet. 1, 2, 3, 4, 5. This is 6 feet. All right, and then what we want to know, what we want to know is what are the values for these reactions from the pin and roller. So we've got our free body diagram. I'm going to move it down a little bit because it's getting a little cluttered with the one above it. So move it down there so it's not as close to the other one. Didn't get the little arrow there. Okay. So I've got a free body diagram. It has the body, which is just the beam. It has all the connections where it was connected to the world have been replaced with just forces. It's got a coordinate system. It has dimensions. It has variables for the unknowns and values for the knowns. It has units. So it's a good free body diagram. Now, I would like to be able to solve for the value for AX, AY, and BY. So I have three unknown things. Fortunately, now I have a new equation to add to my selection of equations, so I can solve for three things. I can actually solve for four if there's something going on in the z direction. This particular problem doesn't have anything in the z direction, so that doesn't do any good for me. So when I only had the concurrent systems, I couldn't use the summation of moments. Now that I know about these moments and non-concurrent force systems, I have a third or fourth equation that I can use. So let's do, there's one here that's like really easy and obvious. Let's do summation of forces in the x direction equals 0. So I look at my free body diagram and I see that AX is the only thing in the x direction. So if I write my equation, that's what it says. Summation of forces in x equals 0 equals AX. Therefore, even though I drew it on there, AX has no reaction. Now in the real world, you know, things start bending and deflecting, and maybe it does have some reaction in the x direction, but we're in the theoretical academic world right now, and so AX is 0. If I say, well, that was easy, let's write the y equation, I can write it, but what it says is AY plus BY minus 1,500 pounds equals 0. And you might think that, oh, well, AY is half of 1,500, BY is the other half. And that can be true, and it's actually close to true in our case for here, but that would only actually be true if the 1,500 pounds was like right in the center of AY and BY. And it's not. It's kind of offset to one side a little bit. So they're not equal to each other. So I need a third equation in order to solve for AY and BY. And that equation is going to be the summation of moment equation. So the deal with the summation of moments is, so for summation of forces in x, then I just look at every force in the x direction. For y, I look at every force in the y direction. For moments, I don't really do directions. I have to figure out what point I'm interested in. So where would be a good point to some moments? What the equation is saying, summation of moments equals 0. What that's saying is that about some point, I know that the body, in this case the beam, is not rotating. It's not, the moments are adding to 0, and it's not spinning around that point. So I know this beam isn't spinning around any points unless I'm thinking of like the sun, but I'm not really thinking of that. I'm thinking, you know, in my local coordinate system, what point, so there's still infinitely many points I could choose. There just happens to be one point that's way better than all the others. So, and this is generally true. It's not a, you know, like 100% true, but if you're unsure, it's probably good enough to get started. And if you have one of these pins as your support, that pin itself, so the point where the pin is, that's probably a good point to some moments about. And so for me, I labeled that pin point A. So to finish my equation, I would write summation of moments about point A. So now I've defined where, and point A is this little point right there where the pin is. That equals 0. I need to add one other thing. So implied in the X and Y is that a direction. You know, X is positive when it goes to the right, Y is positive when it goes up. For moments, I could do the implied direction. Remember, we did the right-hand rule, and so if I move my fingers from where I drew my x-axis to the y, that makes my thumb point upwards, which is positive for a counterclockwise movement. So I could do that. That's probably the more technically correct thing to do. My mind just works better when I do clockwise as positive. So you get to choose which do you want. So most of the time, if you read stuff and look in books and everything, it's going to say counterclockwise moment is positive, and that's technically true. For whatever reason, for me, it is way simpler to do clockwise positive. I don't know, but technically the correct way is counterclockwise positive, following the right hand rule. But I'm usually going to write them as clockwise positive. It's really the same thing as, instead of drawing the X arrow going to the right, I'm just going to draw it to go into the left, and that's more convenient for me for some reason. So that's what I'm going to do. And now I have to write this equation. So the equation is take all the forces that create moments about point A, not every force does, but all the ones that do in my free body diagram, calculate that moment and the summation of all those individual moments. So I have 4 forces that could potentially create moments about A. Those moments all have to add to 0. Now I already know that AX is 0, so it's not contributing because it has no force magnitude. AY is interesting because it is that case that I talked about up here where if my force actually goes through the point, then the distance is 0 and it doesn't create a moment. So AY is one of those cases. AY, line of action, is right through point A. AX is also, so even if AX had a value, it would not create a moment. So AY and AX both don't create moments about point A. That's why it's usually, if you're unsure, that's why the pen is usually a good place, because it's probably eliminating 2 of your unknowns. So AX and AY don't go into the equation I'm solving for, and I'm left with just BY. That works as far as being able to solve for it. So let's get AX, AY. They don't do anything. 1,500 pounds. So 1,500 pounds has a line of action that's assumed to be vertical. I didn't give it any angle and it looks vertical, so I'm assuming it is vertical. So if it's a vertical line of action, then the distance is perpendicular to that, so it's a horizontal distance between point A and that line of action, which I have drawn as 8 feet. Now I need to say, is that positive or negative? So if I look at just the 1,500 pounds and imagine that my little beam here really is pinned, like there's a bolt at point A and it's allowed to spin around that bolt, then which way would the beam spin? And it would spin clockwise. So this, according to my setup, this is a positive moment. So the quantity here is positive. BY, on the other hand, if I look at where BY is, I don't know its magnitude, but the way I drew the arrow, that arrow has a vertical line of action. So I need BY, whatever that number is, times a horizontal, because it needs to be perpendicular to the line of action. Distance between A and B, which is 14 feet, 6 plus 8. And I don't know, maybe by experience I know or whatever, but I just picked a direction to draw BY, and I just picked the positive direction, the positive Y direction. So based on what I chose, BY would make that little beam rotate counterclockwise, which in my equation is negative when it goes counterclockwise. So now this equation has one unknown and a bunch of constants. So I can solve this equation for by. So let me get my calculator. By, well, let's rearrange it. 1500 times 8. So I've got, let me do some intermediate steps here. So I've got 0 equals 1500 times 8 is 12,000. The units on that would be foot-pounds minus by times 14 feet. I want to solve for by, so I need to divide both sides by 14 feet and move by around by itself. So let's do move by times 14 to the left hand side. It becomes positive. 12,000 foot-pounds is left on the right side. Let's divide by 14, not just 14 though, 14 feet. And now by equals 12,000 divided by 14, 857.1, and the units are just pounds. Then I can take that answer, plug it in to my previous equation that had by and ay in it, and solve for ay. These little dots, triangle dot thing, that means therefore. So ay is 1500 minus the 857, 642. So they're not equal, but they're, you know, similar. So the if the 1500 pounds, it's kind of off the top of the screen right now, but if the 1500 pounds had been in the direct center of the span of the beam, so if it had been 7 feet from A and 7 feet from B, then yes, AY and BY would have both been 750 pounds. And you would have calculated the same exact things, and your equations would have told you that, or you could just looked at it and recognize that, well, it's right in the middle, and it's just going to divide evenly. So there is that. All right. Now we at least have a little bit of idea of moments. We have a little bit of idea of solving for reactions, in this case for just a beam. Let's combine all of that with trusses and do method of sections. So let's conceive some little simple truss. I'm going to put these, all those dots are the joints. And all these lines are the members. So in case you don't remember that, there's the joints. The members don't have to be straight, but they most of the time are. But they can be curved and all this other shape. These members are special types of members called two-force members. Well, I didn't talk about it, but you watched a video where I talked about it last time, about two-force members. If you don't remember what that is, then go back and review the two-force member idea. That is important, and it's like central to the idea of the thing even being a truss to begin with. Let's put a roller here. Put a pin here. We'll use the other diagrams than what we used last time, just to have some different stuff in here. Let's put some dimensions. And the other side's just similar to that. So I guess we also have this dimension. That's 2 feet. Okay. And let's say we want to use, well, let's label it. I forgot to label it. We can't talk about it until we have labels on it. A, B, C, D, E, and F. We'll use those letters clockwise, starting at the left hand bottom corner, going around. We'll use those letters to describe member AB or member BF, and that way we can all agree on what we're talking about. Let's say that we want to find this is not a super complicated truss, so method of joints would work fine for this. It wouldn't be much more work than what method of sections is going to be. But let's say that we want to find the force in member BF. So we're given all of this, and we want to find the force in BF. Okay, so method of joints process of doing this would be, all right, we first we need to find, usually first we need to find our reaction. So we go do basically what we did here, but for the whole truss, we replace the pin with forces in AX and AY, place the roller with an EY and solve for those values. Then we probably go to joint A, draw a little concurrent 2D concurrent force system at A, solve for AB and AF. Then we go to joint B. Actually, I guess we don't need to solve for AF. We just go straight to joint B, draw another 2D concurrent force system, and then solve for BF. So a couple of steps to get there. Method of sections, usually you still have to find the external reaction. So what's the pin doing? What's the rollers doing? You don't always have to. There are some like unique kind of situations where it turns out you don't need to solve for that, and you'll better understand that in a minute. Until we talk about some other stuff that won't make sense. But so you still probably need to do the reactions, but before you do that, well, you look for zero force members. That's always a good thing to do. This truss does have one zero force member. If you can't see it, it is CF. CF is a zero force member. Remember our rules from last time for zero force members. You're looking for a joint that has 3 members connected to it. So joint C has 3 members, BC, CD, and CF. There are others that have 3, like B has 3 and D has 3. So all 3 of those could contain zero force members. But then you look at that joint, and all of those 3 members are any 2 collinear. So at B, none of those share the same line of action. That's what collinear would mean. They have the same line of action. So B doesn't have any. D, nothing's collinear. But at C, BC and CD, they share the same line of action. So they're collinear. All right? So C still potentially got a zero force member. The last thing you do is there any external force applied directly to C? And there's not. There's not like some force that's applied directly to C externally. Now there's the internal forces, the forces from the members themselves, but that's not what I'm talking about. Is there external force? And there's not. So if all of those are true, 3 members at C, 2 of them are collinear, no external force at C, applied at C. It doesn't matter if it's applied down here, like, and it's kind of pointing at C. That doesn't matter. It's not applied at C. Then the third one, the non-collinear one, is a zero force member. It is a zero force member when this truss is in this loading configuration. I haven't put any loads on it yet. Let's put some loads on there so it has something to do. Let's go ahead and put one here, and we'll call this 500 pounds, and that'll be enough for the loads. So actually no, because let's practice with our moments and put another one. Let's put 300 pounds here. Otherwise we could just use the the load's just going to evenly divide principle and not have to calculate anything. So by adding this one, we have a unsymmetric loading scenario, and we will have to calculate them manually. All right, so that's usually good to do first. Look for zero force members. Sometimes it turns out the one you're looking for is a zero force member, or maybe it's one of the ones that's connected to the joint you're looking for, and so it helps out. In this case, it doesn't. It it's just good to know. Then when you're doing method of sections, you want to identify the member you're interested in. So I'm going to identify it by doing this. Actually, I'm going to use green. Okay. So the idea with method of sections is that you're going to take your truss and cut it into two completely separate sections. And you want to cut through the piece you're interested in. So that's why I drew the little dotted lines through BF. The catch is you can only cut through 3 pieces, so including the one you're interested in. And that goes back to our 3 equilibrium equations. Now, if you have a Z, if you have a 3-dimensional truss, then okay, you have another one you can work with. We're really only going to do planar trusses, 2D trusses. So in my case, the obvious way to cut this truss into 2 completely separate pieces, cut through the one I'm interested in, and to cut through only 3 is to do this. And so that creates the section part of method of sections. I have 2 sections. I either have the section with joints AB or have the sections with CDEF. So I can work with either one of those sections. And that's how sometimes, if it worked out to where I could chop off a piece of the section, follow all the section rules, and I cut off all the pins and rollers, then I may not need to solve for the reactions. I could just jump straight into what I want to do. In this case, no matter which section I look at, section on AB, there's the pin over there, so there's a reaction I have to solve. Or section CDEF, there's the roller over there, so I have to solve for that reaction. So in this case, I do have to solve for external reactions first. So let's solve, since it's a little bit less, first, let's decide which section we're going to use. I'm going to use AB because there's a little bit less going on over there. If nothing else, it's a little less to draw. Plus, BF is, I get it's in the other section too because I cut through it. So I could use either, but AB looks simpler. So that means I need to solve for the reactions at A. So do not draw only section AB and solve the reactions. When you go to solve the reactions, you need to use the entire truss. So I'm going to cheat and copy this thing. Okay, I'm going to copy all of that. We don't need these. And I'm going to erase the roller, erase the pin. So now it's free in my free body diagram. It is free. And now I need to replace those connections. So there's the replacement for the roller is just some vertical force. It was rolling on horizontal ground, so it has a vertical reaction. The pin at A has 2 reactions. I'm going to put one vertical and I'm going to put one horizontal. I could put them at any orientation as long as they're perpendicular to each other. So as long as got a right angle right there. But I don't have a reason not to make them horizontal and vertical. Now, I really don't care about EY. I've already decided I'm going to use section AB, so I don't have to solve for it if there's a way to not solve for it. I can, by observation, see that all of the forces except for AX are completely vertical. So I just know by looking at it that AX is 0. So when you get in that, it's not always true. It could be that 300 pounds up there is at an angle and now it has a Y, it has a X component. But if you look at everything and you've got one force that is the only one that has any components in that direction, you can just, zero it out. So that's what I'm going to do. Now I need a way to solve for AY. If you do the thing that I said earlier, if you're unsure, just solve for the moments about the pin. You'll actually end up doing an extra step. So think about what goes on when you do the moments about the pin or whatever point. the AX and AY did not show up in the equation because their line of action went through that point. In this case, I want to solve for AY. I don't care about EY. So this one is actually better to do summation of moments about E. I'll do clockwise positive just because I like doing that. And what this equation says that, hey, I know there's a bunch of forces applied to this truss, and I also know that this truss is not rotating about point E. So all of those forces, their moments about point E, add to 0. AX would not be in that equation anyway because AX's line of action goes through point E plus AX is 0. So we don't need that one. Oh, well, equals, equals. There's the AY I want to solve for. It has a 10-foot, what we call moment arm, going around clockwise. 500 pounds. Has a 5-foot. I know I didn't like label the right hand side, but it is a mirror image of the left hand side. The dimensions are. That's a negative moment there created by the 500 pounds because it's going around counterclockwise around E. And I said that clockwise was positive, so if it goes counterclockwise, that means it's negative. Let's erase all these little dots. 300 doing the same thing, so it's also negative. It has a 2-foot moment arm. All right, let's get my calculator out. I've got 500 times 5, that's 2,500 foot-pounds. 600 foot-pounds here. Those are both negative. I have AY times 10 feet. So I'm going to add the 2,500 and the 600 to get 3,100. They're both negative. I'm going to move them to the right side. So I've got AY times 10 feet equals 3,100 foot-pounds. Then I'm going to divide everything by 10 feet, and I'll get AY equals 310 pounds. And I could also solve for EY if I wanted to. I do a little quick sanity check. I have a total of 800 pounds that's kind of shifted over closer to EY. And so EY should be a little bit larger reaction than AY, which it is. I'm less than half of the force at AY, which makes sense because all my external loads are kind of moved over to the right hand side. All right, now I've got a value for AY. So last time, method of joints, we could have gone into joint A, solved for the reactions at AB, or not the reactions, solved for the force at AB, then move to B and solve for BF and be done. But we're doing method of sections, so I'm now going to draw section AB. So there's B, and there's A. There's member AB, and all the other, well, there's the AY I just solved for. Now I do know that this arrow is pointing upwards. I know that because when I drew AY on my free body diagram, I just picked it going up. And then when I solved for the equation based on that selection, that guess, it came out positive. So that means that I did draw that arrow the right way. If I had gotten AY equals negative 3/10, that would mean that I drew the arrow opposite of what it should be. Now these other forces, you can treat them a couple of ways. You could like draw the little pieces that you cut through and then draw the force inside those, or you could just draw the force. Also, until you are like able to look at a truss and say, oh, that piece is in compression, that piece is in tension, or whatever, it's probably way easier just when you're drawing the internal forces, like we'll call this the force in AF, right? And this is the force in BF that we're trying to solve for. and this is the force in BC. Those are the internal forces in those two force members. It's probably easiest just to draw them in tension. And what that means is when you draw the arrow, draw it pointing away from the body. That's just probably the easiest way to deal with it until you can look at a truss and say, oh, member BC is in compression based on this loading configuration. If you can do that, that's fine, and just draw it the right way. But it probably takes a while to look at it and just tell where things are tension and compression. So why I recommend, if you don't know, draw them in tension. That way, when you solve your equations, all the positive values are tension, and anything that came out negative is a compressive force. All right. Let's see if we have any dimensions we can put on here. We do have a little bit. BF is at some angle. I am going to draw it this way. So I'm basically going to say that BF, the member, it's kind of off the top of the screen. I want it to see if I can get it to come down a little bit. There we go. It has a rise of 4 and a run of 3. So I'm looking at my original diagram and looking at, well, there's 3 and there's 4 on the side. So it has a rise over run of 4 over 3. And I can use that as a way to deal with its angle. Also, if I think of it as a 3, 4, 5, the hypotenuse here would be 5, or I could calculate, use Pythagorean theorem and figure out what the hypotenuse of that little triangle would be. Then I'll be able to use it as the cosine or as a sine when I get to it. There's not really, I have other dimensions here. I have this. .4 feet. And I have this. 2 feet. But that's really all the dimensions I have on the free body diagram. I have others based on the actual sketch up here if I need them. But right now I don't need them. So this, let's go ahead and put a coordinate system just to make it an official free body diagram. There we go. There's our official free body diagram of the section AB of that truss. And what I want to do is I want to solve for the force in member BF, which is kind of right there in the middle of our diagram. So I've exposed the force that I'm interested in with one move versus having to do a couple of free body diagrams of different joints when I'm doing method of joints. Now I have access to 3 equilibrium equations. We're not using the fourth one because we're not doing a 3-dimensional truss. So I have access to this, and this. So X, Y, and Z, or well, again, I'm not using Z because we don't have 3 dimensions here. X, Y, and moments. So I have 3 unknowns, BC, BF, and AF. So technically I can solve for all of them. That's the reason, way back up here, that I said when you're making this section, you can only cut through 3 pieces. But you do have to completely disconnect this section from the rest of the truss. So that's the reason for only 3. All right. So now there is often, not always, but probably greater than half the time, often one of these equations that will immediately solve for the thing I'm interested in without having to use the other equations. That's not always true, but probably greater than half the time. So the 2 I'm not interested in, BC and AF, because my problem statement said find BF. So I'm not interested in the other 2. BC and AF, those are completely horizontal. So anything I do with X is going to throw those unknowns into the equation. So I should stay away from summation of forces in X. The moment equation, I don't see a point. So if there was a point where the 2 I'm not interested in, if they intersected somewhere, like at a pin or something like that, then yeah, let's sum moments about that pin and solve for the one we're interested in. But that doesn't happen. BC and AF are parallel, so in our Euclidean geometry here, they never intersect. So that leaves me with Y, which if I look at summation of forces in the Y direction, I have the 310 pounds, and I have the Y component of BF, and that's it. So I can immediately solve for the value of member BF. So let's write the summation forces in the Y direction equals 0. I said that Y is positive when it goes up. So looking at my diagram, 310 is going up. So that's a positive 310 pounds. I drew the arrow BF going down, or downwards. It's kind of going to the right also. So that's a minus FBF. And then I need only the Y component. So I have this 3, 4, 5 triangle thing. I could go in there and calculate, one of these angles. I could maybe calculate that angle, or I could calculate that angle. I could do either one of those. But an even better thing to do is remember that the cosine. Let's do the cosine. The definition of cosine is equal to, or cosine of theta, is equal to the adjacent side over the hypotenuse. And if I'm thinking of this angle here being theta, the adjacent side is 4 and the hypotenuse is 5. So 4/5 is the value of cosine theta. So if I went and found theta, plug, it's I don't know whatever 30 something degrees, 36 degrees, plug in cosine of 36 degrees, I get that definition back. I get 4/5. So I don't know if it's 36 degrees. I don't know what that angle is, but whatever angle it is, I get the value based on this rise over run and the hypotenuse of the little blue triangle I drew. So what I can do is I can skip the step of calculating the angle and say, well, I know the dimensions. So if I want the Y component of it, I just multiply FBF, the magnitude of the force, times 4/5, because that is the adjacent over the hypotenuse side. That's it. Now the only unknown in there is FBF. So therefore, the force in BF equals, move it to the other side, it becomes positive. And I've got 310, and I have to divide by 4/5. 387.5 pounds. It's positive, which means that the arrow direction I chose for force BF is correct. I drew it in tension, so FBF equals 387 pounds in tension. If I'd gotten a negative based on my drawing, then that would mean it's actually supposed to be pointing towards the little free body diagram, which I would rewrite this. Instead of writing negative 387, I would write 387.5 pounds and put a little C in the parentheses for compression. Because this, with the T or C, is more clear than positive and minuses, because the positive and minus depends on what way you drew the arrow to begin with. And some people might just draw the arrows the way they're supposed to be, and then compression is everything's positive if you drew it the way it's supposed to be. And so it's way more clear just to write the number and T or C once you figure out if it's tension or compression. All right. What now? Well, let's see. Let's see if we can find us a problem in web work to look at. Let's go to the optional problems and see if there's a truss in here that looks like it's set up for method of sections. That is not. That's not. We're getting closer. we'll have to talk about these now that we have done moments. This is moments in 3 dimensions. We'll have to talk about those later. All right, here's some trusses. All right, that one's pretty simple. Let's not do that. This one, oh, this one might be good. We can pick out pieces of this one to work on. So let's copy this. So this one actually has some truss calculations, there's reactions, there's stresses, and there's axial deformation, all mixed in this one problem. So this is in the optional set, so it's not one that's required, but this would be a good kind of overall practice problem to work on. All right. Let's draw the free body diagram version of this. So it looks like for me, B is 7 feet and A is 5 feet. I won't draw it to like each one of these boxes is a foot because that'll make it too big. But let's do, so A is the smaller one. So let's do something like this. So there's the top. And then H for me is 8 feet. So let's do something like this. Oh, well, not there. It's over here. And then we'll fill in the middle. So one thing just to make sure you understand on the trusses, these pieces like here, the A, B, and B, C, and C, D, and D, E, those are not one long continuous piece of metal or concrete or whatever it is. Those are individual little segments. If it becomes one long piece, then we're not really drawing a truss anymore. We're drawing a frame or a machine. And so it is important to mentally remember that these are all discrete little pieces. Even when they're all lined up in a row, they're not one long piece. It's discrete little pieces. Okay, there's the truss itself. Let's put our labels on there. Now let's put our forces on it. Well, let's do our reaction. So I've got a pin at A, kind of sideways pin, but still a pin. I don't know those values. The problem doesn't tell me, and normally you don't know those. I've got a roller, so there's a little pin on wheels, and it's rolling on a horizontal surface, so that means that the reaction is vertical. Then I've got F1, 2, 3, and 4, and they're all different. So 10, 20 pounds, 2,000 pounds, 1980 pounds, and 1,100 pounds. Okay. Now, let's look for zero force members. Here's one. So that guy's a zero force member. And that's the only obvious one I see. So I don't see everything else. There's some that like have 3 members and collinear and all that, but they have external forces applied at that joint. So I think only CG is a zero force member. Let's mark which ones we're interested in. So I want to know the reaction forces. So AX, AY, and FY. We'll get to those. I want to know the normal stress in member CD. So I want to know this one. Maybe I won't use a 0. I'll just do that. I want to know change in length of CF, which is that one. And I want to know the change in length of EF, which is actually this one. All right, so this is kind of set up to do both method of sections and method of joints. So it's a little bit of both. So method of sections would be cut right through there and work on just the right-hand side. If the problem didn't specifically say it wants to know the reaction forces, oh, it looks like, let me go back. Oh yeah, it wants to know, so this one's really set up for method of joints. It wants to know the member forces in every member. So it's really set up for method of joints. But we're only doing this little part. These change in length and stress for that. So if it didn't specifically say that it wanted to know AX and AY, then we could just work with this section. Uh-oh, hold on. You're not looking at the right thing. Where is it at? There it is. So you didn't get to see me draw it, and I guess you didn't get to see me select the zero force member CG. But here's the actual picture so that I've been drawing on. So really I was just copying the diagram. I just didn't notice that it wasn't showing on your screen. Yeah, now there's a comment that shows up. All right, so now we should be good. So if this problem didn't specifically say that I needed to find AX and AY, then what I would do is I would look at just this right-hand side of the section of the truss, and I would need to find the value for Fy, but then I'd be done with all the external reaction stuff. So if you're on a test problem, be sure you go through and really check what is the problem asking you for, because none of the problems are going to say, at least none of the problems I give you, are going to say use method of sections to solve for whatever, or use method of joints to solve for this. It's just going to give you solve for this, and it's up to you to pick, do you want to use sections or joints, and what does that mean? Just make sure you know the advantages of using one over the other. The advantages are, if it's on the perimeter, method of joints is probably what you end up with. If it's in the center of the truss somewhere, at least consider method of sections. That's the general rule. All right. Now, let's say that we don't care about all this other stuff. We only want to solve B, C, and D here. That normal stress, change in length, and change in length. We're not interested in solving for every member force. So I'm going to use this section over here, which does mean I need to solve for Fy, so let's do that. I'm going to put that summation of moments. I'm going to do moments about A, right? Because if I only want to know Fy, moments about A gets rid of AX and AY. So it speeds up solving for it. I don't have to do simultaneous equations or something like that. So I do need the whole truss though, and not just my section. So, well, you know what? Now that I look at it, I can't. I do need to do. Oh yeah, no, this is right. This is what I need to do. Moments about A. Sorry. So moments about A. I'm doing clockwise positive. 10, 20 pounds has a. Oh, I didn't write that down. Let's see. Let's put a couple of dimensions on here real quick. So this is 5 feet. This is 5 feet. This is 7. And this is 8. Okay. There. All right, now we can write moment equations. So 10, 20 pounds has a moment arm of 5 feet. The 2,000 pounds has a moment arm of 10 feet. The 1980 has a moment arm of 17 feet. And the 1100 has a moment arm of 24 feet. And Fy, which is going in counterclockwise way, so I'm running out of room. I need this to... Actually, let's put all of this down below. All right, so minus Fy has a moment arm of 17 feet. All of those have to add to 0. If those don't add to 0, then the truss is moving clockwise or counterclockwise about point A. And I know I don't want it to do that, so these need to add to 0. Let's calculate. 1020 times 5. I want to leave the units off. I don't like doing that, but it's getting really crowded with all the units in there, so I'm going to leave them off for now. Now we've got 20,000. I don't know this one. 1980 times 17. 33,660. 26,400 minus FY. Well, let's just go ahead and equals FY times 17. I'll put feet on there. So all of these add together 5,100 plus 20,000 plus 33,660 plus 26,400 is 85,160. Those units are foot-pounds. We'll put them back now. Equals Fy times 17 feet. Divide by 17 feet. Fy equals 5,009.4 pounds. Let's go check that. You know, since we have web work, I'll plug it in and see if we get that right. 5,009.412. Let's see. Oh, no, it's not right. Did I copy something wrong? Let me check my math. Okay. Maybe I copied 5 feet, 5 feet, 7 feet, 7 feet. I don't see error in copying. That's interesting. Did I put it in the wrong spot? Reaction at F? No. Well, let me check here, or if anybody sees what I did that might be wrong, let me know. 1020 times 5. That looks right. 2,000, or let me make sure I got these in the right order. F1, 2, 3, 4, 2,000, 1980, 1100. Those look fine. Those are all. I don't know why WebWork is disagreeing with me on calculating FY. Let me read the problem statement, make sure I didn't miss some weird thing. Yeah, it normally does. I can actually see what WebWork is wanting, and it's not a rounding error, so I'm not sure why it's wanting this number. That's why I was checking to make sure there's not some like, oh, I wonder. So these problems are old problems, and it could be, I'd have to dig into it. It could be that it's actually rounded off some of the numbers it gave me, possibly. you know, instead of 1980, it's supposed to be 1979.6 or something, and it just rounded it to 1980. Maybe that's the issue. I don't know. We'll have to move ahead because I don't want to spend a whole bunch of time trying to figure out what the difference is here. Oh, no, no. Oh, no. Oh, wow. This is one that, no, I did something wrong. But this is maybe a badly set up problem. So look at F1, F2, F3, F4, that's fine. But on the dimensions, B comes before A. So I put it, I just looked at it and like, oh, here's dimension, the first one, that must be A. And I put all the A values, all the 5s on the left-hand side. And they're actually backwards from that. That's unfortunate. So what it really wants is 7 feet here, and 5 feet here and here. I think that's just a badly made problem. Badly labeled problem. The problem's fine, but the labels are like, why not put them in order? So that I guess people like me will check to make sure, learn to check to make sure that where is A and where is B. All right, so let's put those numbers in and we should get the right value. All right, so 1020 needs to be multiplied by 7. 2014. 1980 is 19. FY is 19. And the last one's 24 still. All right. So 7140 plus 28,000 plus, oops, typing the wrong thing, 20,900 plus, this one's the same, 1100 times 24, 26,400 equals FY times, that's 19, right? 14 plus 5, 19. Therefore, let's add all these. 7140 plus 28,000 plus 20,900 plus 26,400. 82,440 foot-pounds divided by 19 feet. Well, did I still type in one wrong? Well, A and A are both 5. Still getting a different number. Wow. Oh, all right. There's the problem. I wrote down the wrong number there. That's a 99160 divided by 19 equals 5218.95 pounds. All right. Check your work. Check your transcription from the problem statement. I will point out that many of the problem statements on the exams are like this, where you have a generic picture with labels, and your problem will have numbers that you have to transcribe correctly onto the diagram. So that was my problem. So there's the issue. 5218 is, yeah, that's what they want. All right. Now, so assuming you do your basic stuff right, then you go to method of sections. We're going to do the right-hand section. So I'm going to copy that guy, paste it. We cut off, what did we cut off with? It looked like this. So we cut this little piece, that little piece, and that little piece. You could go through and try to figure out which ones are tension and compression. I'm just going to make them all tension by drawing the arrows pointing away from the free body diagram. We'll put our x-axis down here and our y-axis up here. And we actually, this problem statement wants us to solve for, what is this? This is CD and CF. We'll call it the force in CD, force in CF. This one's the force in GF or FG. Normally you alphabetize the subscripts, but it doesn't really matter. So it wants me to solve for CD, CF, and it also wants me to solve for EF. That would just be a method of joints at E. You could do that one without any of the reactions. Let's work on the other two, CD and CF. Actually, let's work on CD, because that one's a little bit different than what we've done before. So CD, what they want is the normal stress in member CD if it has a diameter of 0.6 inches. All right, so it's a round, has a diameter, so it's round, 0.6 inches, and we want to calculate the normal stress. Normal stress is force over area, so I need to know what force is in member CD, which is what I've got labeled up here as FCD. So if we can solve that one, we can figure out the stress. So, again, going to my idea of how can I eliminate the ones I don't know. So I don't know CF and I don't know FG. Their names give you a clue. They both have F in them. So if I take my free body diagram of this section, do summation of moments about F, I'll do clockwise positive, then I will eliminate CF and FG from this equation I'm going to write because their line of action goes through F, and I'll have CD show up as the only unknown, and I'll be able to solve for it. So actually FY, CF, FG, and the 1980, all of their lines of actions go through point F. So none of those four different, some I know, some I don't know. Actually, I did solve for FY, so I guess I could put that one in there. 5,218.95 pounds. All of those go through point F. Their line of action goes through point F. Even though the 1980 is not like touching F, its line of action goes through point F. So it does not create a moment about point F. Whenever you have the line of action of a force going through the point of interest, it's the same thing as you go up to a door and you push on the door hinge where it's rotating and the door doesn't move. That's the same thing, where it doesn't create a moment, something that would want to make the object pivot about that point. It doesn't create a moment if you push at the point you're interested in. So 1980, 5200, CF, and FG, all out of the equation. That leaves me with 1100 times 5 feet. So it's a vertical force, vertical line of action. The horizontal distance between that line of action and F is 5 feet. Going around clockwise, so I give it a plus sign. Minus the CD is a horizontal line of action. So I need the vertical distance between that line of action and F, which is 8 feet. And I give it a negative sign because the way I drew it, CD would go around counterclockwise. You know, it would try to pull this section around counterclockwise. Okay, so now I only have CD in this equation. So I can just say that therefore FCD equals, it turns out positive, which means I drew the arrow the right way. I drew the arrow in tension, so it means it's a tensile force. 1100 times 5 divided by 8. 687.5 pounds. They really wanted to know the stress. Sigma equals force over area. They didn't give me the area. They gave me the diameter. And I can calculate the stress. (2,431.5 psi). I'll go plug that into Moodle real quick. Not Moodle, WebWork, and see if we get it right. What was my number? 2,431.5 psi. Yes, it does like that. Okay, I'm just plugging in my other answer so to have it right. All right. All right, I think that probably gets us far enough along with trusses that you can work some homework. I will open up the homework related to the trusses. There is, remember, quiz 1. Let's go to the web over here. Oh, there's my number. Quiz 1 is open. It'll stay open, I think, the rest of this week. Treat that one like a exam. It is representative of the simpler problems on the exam, so you should be able to solve these in, like, I don't know, 4 or 5 minutes each, somewhere in that range, maybe 6 minutes. But treat it like an exam, see how you do. It counts for 2% of your course grade, but it'll give you a good gauge on if you're at least up to speed on the fundamental stuff. The way I build the exams are the fundamental stuff will get you right up to a passing grade, right, on the exam. And so you understand the bare minimum of what statics and mechanics is about. You can still get a higher course grade through doing the work, like doing the web work, doing the optional web work, doing the project and reports well, and things like that. But there will be a number of questions that I consider fundamental that are kind of like the questions on the quizzes, that if you can get those done, then you are you're going to pass the class. You may not make a very high grade if that's all you're able to do, but you'll pass the class. If you are struggling with stuff on quiz 1, then go back and go to the optional web work, do some extra problems. Make sure you've done the assigned web work. Just kind of iterate through some of those practice problems. If you're working in a group, make sure that it's not the group that can solve the problem, but it's you that can solve the problem. Because that's like, that would be like if you went to the gym and you go to work out and it's 2 or 3 of you doing the bench press. You're getting it done, but individually you're not actually able to do it. So make sure that individually you can do the work that you're trying to do here. Exam 1 is next week, right? Exam 1 is on June 22nd. So it's getting close. You still have time, but it's getting close. It does cover through centroids. Centroids are the topic that we'll actually cover tomorrow. So tomorrow's topic is the last thing that'll be on exam 1. And send me. I've seen several emails. I've been at a workshop, so I haven't caught up to all of them, but I have seen several emails about web work and things like that. And I'll start replying to those. And if you have more questions, put them in the Discord, send them to an email, and I'll start getting back caught up with those. And I will see y'all tomorrow afternoon.